Now we need to start from there. So how we might be forgot, right? That to refresh your mind a little bit. We start with when a fluid element will have rotation, when a flow will call only translation. That we try to show you by a orientation or movement of a fluid element. In the left side, like translational flow, fluid element is not rotating about the mass center. But in the right side, fluid element is moving from one point to another point. And while it is moving, it also rotating around the mass center. And sometimes you see in the river, you see there is a vortex. And that vortex is not in same place. Is vortex also moving with the stream of water? If you look in the rainy season in the river or in a canal, okay? Then we try to explain you what is laminar flow and turbulent flow. Then main difference in laminar and turbulent flow. In laminar flow, there is no transfer of momentum from one fluid particle between the fluid particle. But in the turbulent flow, there is a transfer of momentum between the fluid element. Then we should try to show you how you can visualize a flow pattern by simulation and also by doing experiment in the wind tunnel. And if you put some smoke, you can see how flow of the fluid over a object. And you can see all the streamline of the fluid. Then what is the streamline and what is the condition of streamline? If there is a velocity and there is a streamline equation, then which equation it will be satisfied? That we try to explain you. This is the vector, that means distance traveled by a fluid element from point A to B, one point to other point, this point to this point, moving along this direction. And if velocity of the fluid element is this one, then how you can figure out that what condition it will be satisfied? It will satisfy this condition, okay? Then we learn some definition that what is steam tube. It is a imaginary tube for fluid flow where all the streamline is passing from one end to other end of the streamline, and there will be no intersection of the streamline. That and also velocity of the fluid. There should not be any flow perpendicular to the streamline. That is the main characteristics of stream tube. Now, this one will start from here. It's called path line. What is the path line? Path line means the path followed by a fluid element or fluid particle, or actual path traveled by individual fluid particle over a certain time. So it's saying a path line may be defined as a actual path traveled by an individual fluid particle over some period of time, period of time. Okay. Say at 1 second, fluid particle is right over here. After 2 seconds, that means 1 plus delta t is coming along this path right over here, and at time t2 coming over here. So this will be a path line, and a path line can intersect each other. You see this fluid element passing along this line and this fluid element passing over this line. Now, you might have the question that when a fluid element coming over here and other one coming, is there is any collision? If there is any collision, then fluid path or path line of these two fluid elements will be changed, but there is no collision. Why? Because they are traveling not at the same velocity. So this fluid element might be cross this line, came in over here, then this fluid element cross his path. Okay. Although their path is intersecting each other, but there is no transfer of momentum. Right over here, a fluid element might come back or passing through the same point several times. This fluid element coming, he crossing this line, again he's coming right over here, then going to the downstream. Okay. So two path line can intersect each other, or a single path line can form a loop as different particle or even same particle can arrive at the same point at different instant of time. For example, fluid particle from here, at a time he came in over here. Then he crossed this point again after few seconds, he again come back over here. Some case it might be make a loop again, might be making a loop, not following the same path, but might be in this one. Then he traveling along this way. So you just need to understand what is the path line. The path is it is a trace of line followed by a fluid particle, or path travel by a fluid particle over some period of time. Then other thing is streak line. What is the streak line? You see, sometime your younger brother might be, they play with the bubble, water bubble and soap. So you see the fluid particle, or if it's a bubble, you release 8 bubble, but all the bubble, like this is bubble 1. What was his initial position? His initial position was right over here. Then he came in over here. Gradually, he followed 0.657, then came in over here. Second bubble, that means this one. He also followed the same path. It's not like that, that the first bubble following this path and second bubble coming along this path. No. So it's saying streak line is the locus of the temporary location of all particles that have passed through a fixed point in the flow field at any instant of time. So how do you see over here? That all the fluid elements, they are passing through a fixed point. That is the main definition. Or you can say it is a line traced by a fluid particle passing through a fixed point in the flow field. Okay. And usually you can easily observe, say you make a, there is a wall, say right over here, vertical wall. You have a window or door in the balcony. You play with the water bubble and release the bubble. You might observe the all the bubble, some until some time they are passing through the same point, going through the same point. That is called streak line. Then timeline. What is the timeline? Timeline is a set of adjacent fluid particle. Adjacent fluid particle means, say, I have a group of fluid particle, and after time t, how they travel along the stream. So this fluid particle, his velocity almost zero because he is close to the wall. Same thing for this one, but if you consider the fluid particle from the wall, little bit away from the wall, this fluid particle travel this much distance. This one travel this much, this one travel this much. So what did you see? They all of the fluid element along the adjacent fluid element, they take the same amount of time, but they don't travel same distance. So at a time t1, this is their distance travel by the fluid element. So if you connect this line, then this line is called timeline. This is timeline over time t1, say 2 seconds. What will be the timeline after 5 seconds? That will be like this one, he will travel, might be this much, this one might be this much. So, excuse me, or might be this one is this much. So, if you connect all the line, then this line is called timeline. Okay, so what is the definition? Timeline is a set of adjacent fluid particles that are marked at the same instant in time. Timelines are particularly useful in situations where uniformity of a flow to be examined. You like to check whether there is uniform flow or not. Then you need to check the timeline that you have a, for example, glass tube and the fluid flow along this direction. So you are put some dye, if you put some color in the fluid right over here, then you just sitting over here. Then you counting, a fluid particle came in over here within 2 seconds where it is going. So he might came right over here, this one might be came right over here. This one might be came over here, this one might be. So what you see over here, their velocity is not uniform. But if they are travel almost by the same distance, by the same amount of time, you can say your flow is uniform. So that means this region flow is uniform, but this region flow is not uniform. So you can figure out that where flow is uniform and where is non-uniform. Okay. Over here, just I try to show you the difference. Sometimes I put question that what is the difference between streamline, streak line, and path line. Okay. So path line is a flow path of individual fluid particle with time exposed flow. That means you have to consider the time, not the velocity, but you have to consider the time. Then within 5 seconds or within 2 seconds, the fluid particle, how they are traveling in the fluid, in the or in the stream, and you make that line. That is called path line. And streak line, it's saying instantaneous snapshot of a time integrated flow pattern. That means after you release, immediately you have to look that how they are flowing in the stream and following a fixed point. All the fluid element. That is called streamline. Streamline are instantaneous picture of the flow field. That means based on the time. What is the definition of the streamline? That every point you make a tangent, that tangent will give you the direction of the fluid particle. Say you have a streamline like that. So a fluid particle coming from here, he coming over here. So along the east line, if you make tangent of here, this will give you direction of the velocity. So everywhere, every point, fluid element is changing the direction of velocity. As per I draw it over here, right? So over here, this is streamline, and it's a path line and streak line are flow pattern that have a time history. But streamline, there's no time history, but it has a time history because every time you're giving the velocity, right? Velocity also related to the time. So path line and streak line or flow pattern have a time history associated with them. So just remember the differences. And sometime I put this question in the exam, I see everyone just write down the definition instead of giving the difference. Okay. Okay. What is the fluid mechanics? We will apply some law of engineering mechanics to the fluid, right? So in engineering mechanics, you will have three law, right? Like principle of conservation of mass, that you cannot create or destroy mass. This is one principle, and we'll use this principle and we'll derive a equation based on this principle. That equation is called continuity equation. Other one, principle of conservation of energy. That means energy neither be created or destroyed. On the basis of the principle, I will derive energy equation in the fluid. Might be not, okay, because it's a little bit bigger, but we will show you how we can derive and what is the final equation, energy equation of fluid. Principle of conservation of momentum or impulse of momentum, this one, okay. So impulse of the resultant force or product of force and time increment during which it act, it is equal to the change of momentum of the fluid. And on the basis of this principle, we will derive momentum equation. What is that equation? If you know the Newton's second law, that F equal to ma. And this one, we can write down A equal to dV by dt. And this dV, we can say V2 minus V1 divided by time dt. And from here, you see, we can write down that F into, or only you say into dt equal to m into V2 minus V1. So what is V2? What is this portion? Right hand side. Right hand side is actually the change of momentum. And from this change of momentum, we will figure out that if a fluid passing through a pipeline, then if he change the direction, then what will happen? If fluid elements change the direction or flow, so change the direction of the velocity. That means this V is changing in terms of direction and magnitude. Then there will be some force. I need to figure out how much force will be there. For example, you working Dhaka City Corporation as a mechanical engineer, you design a water line and they're making this way. So right over here, change of momentum will be high, right here will be high. And if there is any 90-degree turn of the pipeline, then there will be also high change of momentum. So in this area, due to change of momentum, the fluid will impose some force on the pipe. And you need to make sure that support of the pipeline has to carry that force. Okay. So, and we'll derive that equation. We'll show you if there is a change of momentum of the fluid, how we'll get a force. This is just continuation of Taylor series that we will use throughout the fluid mechanics, that if you have a rho at a certain point, how can figure out the density at a distance dx x by 2 from that point. Dx by 2, in that case, this will be the density. Similarly, if you like to figure out the velocity, by using Taylor series, we can figure out. Okay. Same thing we are showing over here. Okay. So right over here, you already know that conservation of mass equation. That means mass entering in a control volume, say a water tank, and water is coming from the by the pump from the ground floor. Then water is leaving through the pipe coming to the east floor of the house. Now, how much mass increasing inside the water tank? How can figure out? You can figure out mass entering per unit time, right? That mass in minus mass leaving per unit time. Mass leaving per unit time, what is called? Normally, we call it m dot. That means it's expressed by m dot. Mass per unit time, that means mass flow rate. So we can say m in. And mass getting out, we can say m dot m out. That means this mass is getting out from the control volume, and this mass remain coming inside the control volume. So how much mass increasing? So you can just figure out m in minus m out, right? So m in minus m out will give you increase of mass in the control volume per unit time. And if it's steady flow means mass flow is not changing respect to time. Then what will happen? Inside the control volume, there will be no change of mass. Same amount mass entering in the control volume, that will be get out in the same amount of mass will be also get out from the control volume. That means your water tank will not be fill up, right? Though you are entering, pushing some water by the pump, because you releasing 2 liter per second or 5 kg per second, same amount of water getting out from the water tank. And definition, you know, the matter cannot be created or destroyed, but you can sense in different form of matter. This principle is known as conservation of mass. Okay, and also sometime we need to use this principle to derive the energy equation and also continuity equation. So let's derive the continuity equation for two-dimensional flow. Say there is a pipeline and fluid entering at section A1 and leaving through section 2. So in the section 2 area A2, velocity of the fluid U2 rho 2. That means is compressible. You see rho is not the same. Right over here one density, at the section 2 there is a other density. Now we are saying that mass cannot be created or cannot be destroyed. And since there is no storage, right? So water entering in the pipeline at section 1 and same amount of water has to leave through point 2. And water entering over here in section 1, how much? M dot. M dot in, this will be M dot out, right? So in that case, we can say that M dot in equal to M dot out, right? Or we can say M dot 1, M dot mass flow rate at point 1 will be equal to same at mass flow rate at point 2, because mass is not leaving through the boundary. So same amount of mass has to leave the system. Now, how will figure out the mass flow rate? You see, we know the velocity of the fluid element. Velocity of the fluid element at section 1, U1. And area, let's say A1. Or if you think the small section, area del A1 and velocity E1. And I already, I think I show you that if you multiply the area into velocity of the fluid, then what will you get? You'll get Q. That means volume of water flowing per unit time. You say area, unit of area, meter square, right? Meter square. Unit of velocity, meter per second. So finally, you are getting meter cube per second. That is called volume flow rate, or sometimes it is called only flow rate. That is, we express by Q. Okay. Now, what will be unit of Q? Meter cube per second. But I need M1. So if meter cube per second, that means Q, if you multiply by rho, then what you are getting? Q is the meter cube per second. Then you times by density. Rho is the density. Kg per meter cube. Then you see meter cube will be cancel out. So you will have unit Q equal to kg per second. That means area into velocity into density, you will get the mass flow rate. So right over here, you are getting rho 1 into del A1, or you can say only A1. U1 equal to rho 2 A2 U2 equal to mass flow rate, and that is constant in that case. So this is steady flow. That's why mass entering this point is the same. But if is not the steady flow, that means flow rate is changing respect to time. Right over here and right over here, then some mass will be remain over here. But we are thinking for a steady flow. So in that steady flow, you are getting this one. Now, if density is constant, in that case, rho 1 and rho 2 will be the same. So then you are getting only this equation. A1 E1 equal to A2 U2 equal to Q. So this is called continuity equation for two-dimensional, one-dimensional flow going on one direction, and fluid is not uh, compressible. Okay, that means incompressible. And this one, sometime we write down this way that 1 second, we write down like Q equal to area at section 1 multiplied by velocity at section 1 will be area 2 and velocity at area location 2, and this equal to constant. So what happened? If you know the velocity at point 1, if you know the area, and other point, you know the area, then you need to know the velocity, how you can figure out. Directly you can figure out if you know the area, because V2 equal to A1 V1 divided by V2. From here, I can write down V2 equal to A1 V1 divided by A2. Okay, this is. Any question? Hello?
No, sir.
No. Okay. Now we'll derive a equation uh, that also continuity equation, but for compressible flow. Compressible flow mean, anyone know what is compressible flow? The rho is not constant. That means rho changing when fluid flow from one point to other point. That is called compressible flow. And in compressible flow, fluid density is constant. So if I think a fluid element, say a rectangular fluid element I am considering, or a control volume. Okay. So if I choose this control volume, and at the center of this control volume, fluid element has a density. So I'm saying this is the center. There will be density. And if I draw the axis, then this is vertical axis, horizontal axis, this is third axis. So fluid element will have three components of velocity: U, V, W. And density at the center is rho. And this fluid element has some dimension, dx, dy, dz. What will be the mass? We can figure out easily, right? We figure out the volume. Volume will be dx, dy, dz multiplied by the rho. You get the mass, right? So if velocity of fluid element at the center of the control volume is this one, then you see rho when right over here is not the same as center, also right over here. So I'm thinking that some fluid entering along x-axis and leaving out from the control volume. Similarly, some fluid entering from the bottom along, say from the top, from z-axis and leaving through the bottom. Similarly, along other axis. Okay, now at the center along x-axis, what is the velocity of the fluid? U. So at the center, I have velocity U and density of the fluid rho. So what will be the velocity right over here? Is not the same U, because it also changing. Similarly, right of her is not the same as this point, it is also changing. But how I can figure out the velocity at this point? Again, by Taylor series. In that case, my h will be how much? This much distance, right? Dx by 2. So from here, I can figure out the velocity and density of fluid at inlet and also at outlet. And we know the outlet area. You multiply dy by dz, you get the area. So area, the area, the velocity along x-axis. So I'm saying x. Then you multiply by the density. Then what are we getting actually? A V rho. That means you are getting mass. Rho A U. That means density, area, and velocity. You will get the mass flow rate. Okay. Then mass in minus mass out. What will get? Mass remain inside the control volume. And we'll do this along all the axes. Like along vertical axis, right over here, what is the velocity of the fluid particle? V. And that velocity at the top, at the bottom is not the same. They're changing. Also rho. So rho is changing respect to y direction, and along x-axis, rho is changing respect to x-axis. And we'll figure out what is the mass deposited inside the control volume due to the flow from y-axis. Then all the mass, net mass from x-axis, y-axis, z-axis will sum together. Then we'll figure out the rate of change of mass inside the control volume. Then we derive the continuity equation. Okay. So let's derive that equation. Before that, you have to write some assumption. Okay. Consider an infinite small control volume of dimension dx, dy, dz. Density of the fluid at the center of the control volume is rho, and velocity of the fluid v. V is the vector. It has a 3 component. And we'll assume ideal fluid. That means no viscosity and fluid is incompressible. Okay. This is 2 assumption. So let's we can derive this. Before we start derive, any question so far? No? Okay. Let's say one thing that sometime I see attendance is extremely low, but don't forget it is completely 10 mark. And in the last semester in my class, I think about 10 or 12 only got A plus. And I see some people got like 76, 77, but 3 mark is not able to increase because they don't have any attendance. Like from out of 10, they got 2 or 3 mark on the attendance. So request your friend to attend in the class, and from the next week, I might take attendance by calling you after 10 minutes or 15 minutes, because I see that some student, they that join in the class just before 10 minutes, 15 minutes. What does it mean? They just join in the class to get the attendance, but they're not staying in the classroom. Okay. So if I call you, but still you are not response, that means you are not in your screen. Then you will not get the attendance. Okay. Okay. Now let's derive that continuity equation. Okay. Wait 1 second. Okay, did you see the equation and mathcat file?
Yes, sir.
Okay, so let's see how we can derive. Uh, it's a derivation of continuity equation for compressible flow. Consider an infinitesimal control volume with side length dx, dy, dz, density of the fluid at the center of the control volume, O. O is the center of control volume. Right there, density is rho and velocity of the fluid particle vector V. That's why I just bold it. Okay, and this is the velocity vector. So right over here, along x-axis, some mass entering in the control volume and mass getting out. And what will be the mass deposited inside the control volume? You can say m in minus m out, right? And right over here, I just try to show you that if you multiply q into rho, how will you get the m dot? That's showing at the unit. And m dot is called mass flow rate, unit kg per meter second. Okay. Now, density of the fluid is not constant. It varies based on space and time. What is the space? Respect to distance, x, y, and z. So density of the fluid, left hand and right side of the cube is not the same. Right over here and right over is not same. So we need to uh, figure out the density at left side and right side. Why? Because I need to figure out m dot. And how will get the m dot? Equal to rho into q. And what is the q? Area into v. I know this area, y dz into yz. And I'm sorry, y. This will be area. If I know the u, that means velocity, and the density, then I can figure out the m dot. Okay, that's the intention. So right over here, I was trying to show you by Taylor series. This is my Taylor series. So at the center, density is rho. Right over here is rho. So what will be density at distance dx by 2? So just fx will be rho, and this is you put dx. So you put this on, then we are getting this equation, this one. And this higher order term, dx by 2. Dx is very small term, you divide by 2, then you are squaring more, getting smaller. So we can neglect for simplification. Again, that means we are missing some accuracy, how we can justify by experiment. So now your density of the fluid element at the right side, right over here, x plus dx by 2. Why dx by 2? Because distance from the center of the fluid element and right is this much. So this distance, how much? Actually, this distance is dx by 2, positive, right? But what about the distance from leftist, center to leftist? That will be this much, right? That means minus dx by 2. You need to travel negative x-axis. So left side of the fluid, this is my density. I'm sorry, this is right side, positive. Left side, this much. So we have the Density, already got it, right? Now we need to figure out the velocity of the fluid at these 2 points. How we'll get the velocity? It says similarly, velocity component U at the right and left side of the control volume. So at the right side will be this one. Here, instead of rho, you just put U because you looking the how U is changing. Okay. Then this one is U at left side. The distance is dx by 2, but this is minus. That's why you put minus over here. Then I need to figure out m dot in and how much mass entering right over here. So if you like to figure out m dot in, okay. So what I need? I need velocity at the left side. This is my velocity, left side, this one. Density at the left side, density right over here, we figure out. Into area, left side area dy into dz, this area. Similarly, now this value, what is this value? This equal to this mass, and this equal to rho. We just figure out over here, rho equal to this mass. So we just put over here. Then you just multiply, take out the bracket. So u into rho, and u into this term, right over u, and this term remain the same. Then by this term, so this term into rho, so this term into rho, minus minus plus. Then you are getting this term multiply by this term, multiply by this term, that over dy by dz. Okay. Now dx square. So we can neglect this term, higher order term. And right over here, you multiply by dy dz. So you are getting rho u dy dz. Then right over here, just rearrange. Like u and d rho, I keep in a bracket. Half, this is volume dx dy dz. Similarly, this one is neglected, right? You just rearrange this one. Half rho du by dx, you have this term. Okay. Now, if you look carefully, that this half I can take it out from this two term, dx dy I put in a bracket. So inside u rho del rho by del x and rho del u by del x. So if we look this term equal to actually del by del x del rho. Could you hold on 1 second, please? Hello. Okay. Are you able to listen me?
Yes, sir.
Okay. So we are just right here. We like to figure out that how much mass is entering through uh, x-axis at the left side. So after rearrange, we are getting this term. If you look carefully this term actually derivative of rho u by del x rho u, or derivative of uv. So like this is u, then del v by del x, then it is v del v by del x, right? Instead of v, we have rho. So this term, we can write down del by del x rho del rho. ठीक है sir? Okay. Now, so this is m dot in. Similarly, we need to figure out the m dot out, that how much mass is getting out from the right side, this m out. Similarly, m out will be equal to density into velocity into area. So you see, this is my velocity, this is density, and this is the area. Similarly, you put all this value equal to this one, we already figure out, and density right side, this mass, and this is the area. So similarly, you multiply and rearrange, then you will get just this term. This is your m dot, and this is our m dot in. So if we take the subtract of these two, we can figure out that how much mass remain inside due to the velocity component u. So m dot x net, in the exam, you will write down like that: m dot x. In this program, I am not able to write dot at the top. That's why I did like m dot over here. Then you say m dot x net. This equal to how much? You write down this. You write down m dot x in. That way I write down over here. Okay. So you subtract these two value, m dot x in, m dot x out. So this is the in, this is the out. We already figure out the show you, right? Then you rearrange this equation. Then you see this term will be cancel out. This is cancel out. So you'll have m dot net, this term and this term. Okay. So if you look carefully, this is, if I say half x, this is half x, what will get? Full x. This equal to minus del by del x by this component. Okay. Similarly, along y-axis, you are getting this one. Or similarly, for m dot y net, we need to figure out. So m dot y net will give you, if you follow the same procedure, instead of u, you're getting v. So this is my m dot net for the velocity component v. Similarly, you can figure out m dot z net. That means along this direction, this will be this term. Now, what will be the change of mass inside the control volume? Change of mass equal to del m by del t, right? So del m by del t, then what will be the m? Volume into density. So this is the volume and this is the density. Volume is not changing respect to time, only density is changing. So this one I can write down del rho del t into volume. Now, what do you see? This mass increase or decrease inside the control volume. So if I make summation or m dot net along x-axis, y-axis, z-axis, that will be equal to this term. Okay. So you see m dot net along x-axis, y-axis plus z-axis equal to m dot sense. Now, this one we already figure out, minus this term. That means mass deposited into the control volume due to the velocity component u. This one due to the velocity component v, and this one due to the velocity component z, equal to rate of change of mass right over here. Now, you see dv is everywhere. I can take it out. So finally, you are getting this equation. Del by del x rho u, del by del y rho v, del by del z rho w, del rho by del t equal to 0. This equation is called continuity equation for compressible flow, three-dimensional flow in rectangular coordinate. And similarly, you can figure out for cylindrical coordinate or spherical coordinate. Okay. And this equation you can apply for steady, unsteady, uniform, non-uniform, compressible, and also for incompressible flow. If you think that fluid density is constant, that means incompressible. So in that case, this component will be 0. If you say fluid is steady flow, what does it mean? Nothing changing respect to time. That means this will be del rho by del t will be 0. If you say flow is two-dimensional, what does it mean? There is no W, W is 0. If it is one-dimensional, that means two velocity component will be 0. So this equation we can use for both compressible, steady, and incompressible flow. Now, this equation, some book, they represent in the other way. You see, you spend a lot of time to learn the mathematics. What is the application? Right over here. You know divergence. See right over here. Sometimes called deep V. This one I write down over here. Deep. Divergence. And this is the V. If you make dot product, these two vector, this one and this one, rho v equal, you will get this term. At first, in this v, we multiply by rho. Rho is not the vector, right? Just fixed, multiply with the rho, a constant, for example. So it will be rho u, rho v j, rho w k. Now, this vector, this one, div and the rho v, you make the dot product. Then you get this one. Now you see left side of this term I can replace by this one. So equation 1, that means this equation I can write down with this way. At first, we rearrange this equation. Write this one. Okay, we rearrange it. Then we got d rho v del rho by dt. Okay. So far, any question? Hello, in the derivation? No question? Anyone?
No, sir. No question.
No. Okay. So we'll show you that how you can use this equation for steady, then incompressible flow, also for one-dimensional or two-dimensional flow. So let's see where I left it, right over here. So this is the derivation, okay? So if I put this derivation in the exam, make sure you start from the assumption. Okay, now I'd like to show you something else, that this continuity equation, how we can use for different case of flow. So this is my continuity equation, and this is a time derivative, changing respect to time. So for steady flow, nothing changing in respect to time. So this term will be 0. Then here continuity equation coming. This one, if you like to express in simplified form, then you can say divergence of rho v equal to 0. This one is called divergence. For incompressible flow, again you have no sense of density, right? So this equation, this will be 0. Then this rho is constant, right? You rho take out the outside. Then what I am saying, that right over here, if I take this line again, writing over here, since rho is the constant, I like to take that rho out of the take common, and this term is already 0, so I can delete this term. Now I miss the row, right? So this row will be this one. Okay. Now if you want, you can take out this bracket from with the velocity component. So ultimately, what will happen? This row, this term, row cannot be 0. So this term equal to 0. That's I write down. Quantity equation become this one. And if incompressible, and you say flow is two-dimensional, then what will happen? W equal to 0. Then in that case, your this value is coming 0. Okay. And you see, for incompressible flow, rho is not changing. Again, rho is not changing along x-axis, along y-axis, along z-axis. Even rho u, if you this term, you can break in two terms like this one: rho into del u by del x plus u into del rho by del x. Then what will happen? Rho is not changing respect to x-axis, so this will be 0. So only we have only this term. So this is the continuity equation, and for one-dimensional flow, obviously these two will be 0. So you have only this term. For one-dimensional incompressible flow, no change of density. So you have only this term. And what is getting ultimately? Rho you taken outside, rho cannot be 0. Then you are getting del u by del x equal to 0. That means velocity is not changing with respect to x-axis. So this is just to form, I might say, derive the continuity equation. Then what will be the form of continuity equation for incompressible, steady, incompressible flow? Then you just to show that what will be the equation. Okay. No question? Any question? If you have question, let me know. Okay. Now, this continuity equation we derive in Cartesian coordinate, right? That means only x, y, and z coordinate. But this continuity equation also can be derived for a spherical coordinate system. For example, you like to figure out the continuity equation, or you are in space, NASA Space Center, and you are studying the airflow around the outer periphery of the world. So how we can study? This is a Earth is round, and from space also you see the round, right? So if this is Earth, there you need to study the about 2 mile above the Earth, the atmosphere. You counting that what is the air velocity, how it is look like. Then you need to use the spherical coordinate. That is the spherical coordinate. You see, I think this is in the math class, but still I put it. In spherical coordinate will be r, theta, phi. What is the r? The radius. Also theta vary in the bottom, x and y in plane axis. And this phi is the angle between vertical axis. So if this around the sphere, r, theta, phi will vary. R is 0, you are getting at the center of the earth. R is right over here, you are just top surface of the earth where we live. But if you increase the R, you will be in the atmosphere of the earth, right? And for different location, you can change this angle, rho and phi. Okay. And right hand side is called cylindrical coordinate. Say you have a pipe flow. You like to study a flow of air inside a tube or inside a pipeline or submarine, inside a aircraft body. How look like a aircraft body is not perfectly cylindrical, but somehow you can simplify as a cylindrical body. Then like boiler, you like to study the water flow inside the boiler or flow of steam, then you need to use the cylindrical coordinate. In that case, your coordinate will be r, phi, then z. Okay. So don't be scared. I just refresh you, and I like to show you what will be the form of continuity equation in these two coordinate. Normally we I derive these two equation, but here we will not derive. I will just give you the continuity equation in cylindrical coordinate. So this is the form of continuity equation in cylindrical coordinate. Okay. In spherical coordinate, we don't have the, I don't give you the equation. Okay. And this one we could derive, but it will be little bit uh, in-depth analysis. So I skip it. So in the exam, I might say derive the continuity equation for compressible flow and deduce the equation for steady two-dimensional flow. Then I might say write the continuity equation in cylindrical coordinate. Okay. So this chapter is finished. Okay. Now we will start new chapter. Did you see the screen?
Yes, sir.
Okay. Don't be scared. It's easy. Okay. But one thing is here, both here.
Yes, sir.
Okay. I will have 3 more week, right? Including
Yes, sir.
this week. So I am not sure that I able to finish. Normally, I need 3 extra class to finish the chapter, syllabus in my part. So in that case, last 2 week, you have two options. You can give 3 extra class, or you can have class both together. So I don't have to repeat. Instead, I can move forward. In that case, you guys need to decide. You need to talk each other, then you need to decide. Okay?
Okay, sir.
And let me know by next class, or you can email me. Okay. This chapter is little bit like previous lecture sheet. We derive the continuation equation, how it look like. Seems like you are in a math class, not in the fluid mechanics class, right? But fluid mechanics is highly mathematical term is used. If you do masters or PhD in fluid dynamics, then most of the time you have to use the differential equation. You have to use different boundary condition, then you solve it, then you look that solution of the differential equation is right. How you can know? You can then do the simulation in the ANSYS. I think I already told you before that in fluid dynamics class, I took one class when I did masters in UTA. There was a one teacher. He was showing the differential equation, and in the that he was showing, say you are he was teaching us combustion, but what is the nuclear bomb? Is kind of combustion of uranium, right? You drop it, due to the impact, it start combustion and it explode. So in that case, he was showing that uh, derived differential equation to figure out if you a bomb from a certain distance, then at first it will be like a mushroom. There will be height of the mushroom. There will be radius right over here. And how long take time to have 20 feet steam height from here to 20 feet? How much time needed to have a diameter of 5 meters or 2 miles? Then what will be the radius of this portion? And how the flame will travel around the peripheral direction? What will be the speed? What will be the temperature right over here, and right over here? Everything you can derive with differential equation, fluid mechanics. So what I'm saying that you should not be scared. This is the scope. You see, you learn math in intermediate, in school, also in the when you are studying engineering. On your first year, second year, you might say, why are learning math? What is the application? So here is the application that you have already seen in the previous slide, right? In to derive um, continuity equation. So similarly, right over here, we will derive some equation by using differential equation, also using the math. Okay. So right over here, I just trying to show you that a fluid element at time t, right this point. Then after time delta t, it deformed like that. So actually what happened? If you try to visualize, try to understand, you see at first, I am saying that this fluid element, he think this corner, this corner travel from this point to this point. He came in over here. So what does it mean? Just translation. Then you see orientation is not the same. Then he make a rotation. You see this line go up, this line moving upward, right? And this line move along this direction, y-axis, like it was vertical, right? But he rotated. So then he rotated to match with this orientation. And after rotation, he has some angular deformation. So you see right over here, he rotated, but there is no angular deformation because all the side still vertical. But right over here, he has angular deformation. After angular deformation, then there is a linear deformation. That means his one side become bigger than the other side, but length increase. So finally, he become this shape. Okay. So a fluid element, when a fluid particle is travel in the fluid stream, then there might be rotation, there might be translation, there might be angular deformation, and also might be linear deformation. If there is only linear deformation, then there will be no vortex, there will be no curve. But if there is angular deformation, then there will be some vortex. For example, if you burn mosquito coil, then you see smoke coming out. In one stage, you will see smoke is making a vortex. Similarly, if you look carefully, somebody is smoking, then fluid coming out, smoke from the cigarette, at that point it is rotating. So you need to figure out mathematically when there will be rotation, when there will be no rotation. Okay, that we will try to figure out. And this slide I already put again, already discussed it to refresh your mind, but we will not discuss it again. Okay, now So three type of motion we'll have in the fluid. Number one, rotational, there will be rotation. And this is called pure or irrotational translation, when there is no rotation, only translate a fluid element from one point to another point. And this one is rotation. And what is this one? Angular deformation. This one. And this one, if I consider a fluid element, this is the initial position. And after time del t, he might come back to this shape. That means there is a angular deformation in the fluid element. Okay. Now, you need to figure out why some cases fluid element traveling from, I'm saying, from this point to this point and shape is changing. What is the reason? The reason is that this point O traveling with the same velocity, certain velocity along x-axis, along y-axis. So along y-axis, velocity of the fluid at point O, say u, but velocity, I'm sorry, say y-axis velocity v, but point A, how many velocity he has? Two component, u and v. So his v is not same as this v. So I am saying his v is va. So in vertical direction, point A travel faster than point O. That's why you see, this is my point O, this is my point A. So point A move faster along vertical direction. But how to know if fluid element del x velocity is v over here, what will velocity at point A? Easily you can figure out by Taylor series. Then you multiply by time, then you can figure out this distance, the how much he traveling faster. Okay. So let's see, we'll derive one thing. Okay. So there is rotation or rotational translation, pure distortion, or there is called also angular deformation of the fluid. So we'll check it that when there will be translation, what is the condition for translation? What is the condition for angular deformation? You see, if there is a angular deformation, what does it mean? That means there will be a vortex. So mathematically, you can prove that there will be vortex and there will be no vortex. You can mathematically prove. Okay. This one just this one more point I added over here. This is called shear deformation. This is elongation. This is called dilatation. That means you see this like dilatation kind of a drop or the rain drop dropping coming through the air. It hit the ground, then what will happen? It expand, right? Is volume no more spherical shape. That is called also dilatation. That means a fluid element initially at a time t is cube, then still he is cube, but his volume is increasing gradually. Okay, and how the bubble burst in you see bubble, soap bubble. It has the pressure inside, then it has a pressure outside, right? When both pressure is same, it will not burst. Any reason, inside pressure, outside pressure is different, then it is burst because his skin is kind of film, little film, right? So you can also figure out by differential equation in the fluid dynamics that how a bubble coming at a certain speed through the air and when it will be passed and how its shape will be changed. Okay, but we'll not study that. I should not scare you, and we'll derive some equation. It's called linear translation. When there will be a linear translation and linear deformation of fluid element, that will check it. Okay, so we have the time, right? Oh, almost a little bit time we have. Okay, 1 second. I think we can finish it. Okay, we'll try to show you that mathematical relationship or equation that when there will be linear translation, when there will be vortex in the fluid flow, that will try to show you. Okay, so a fluid element is a black one. O is the left corner, and it has 4s, right? And this fluid element has a velocity at point O, u v w, and it is moved from point O to O prime, but with time, small time dt, but shape is not changing. Okay, so if u component velocity along x-axis is u, then how much will be this distance? This distance obviously will be u into delta t, right? Because x velocity divided by time, you will get the distance. Similarly, how we can figure out the distance travel along y-axis by point O. So y-axis velocity is v into delta t. Okay. There is no only linear translation. There is no deformation. But sometime you might see fluid element is like that, but he came in over here, then he's deformed like that. On length getting bigger. That we need to figure out a differential equation in that what will be the condition if there is a linear translation on linear deformation of the fluid element. So you see right over here in the a fluid element at a time t is right over here. His dimension OACB. But after certain time, what is the time difference? Delta t. T plus delta t time, he travel from here to here, become OB A prime C prime. A prime C prime is the new position of line AC. That because he get bigger, this much bigger, right? Now you need to derive the mathematical equation. You see how much his dimension increase along x-axis. Dimension increase only this much. If I know this length C to C, this length, then we can figure out that how much length increase in x-axis. Similarly, we figure out along y-axis, along z-axis. Then you will know the how much volume is increasing, total volume. Now you look, the velocity of point O along x-axis is u. That is right over here. and this is U. Velocity of the fluid along y-axis is V. That will be right over here. But there is no changing dimension along y-axis. What does it mean? That means line O and point A, they are traveling with same speed along y-axis. Then point B and C traveling along y-axis, vertical direction with the same velocity. But in x-axis, B and point O, they have velocity U. But C and A, their velocity is different, higher than point O and B. So if point O velocity U, what will be velocity at point A? Same thing, you need to use the Taylor series. What is my Ace? Ace is the del X. So U plus del U by del X into del X. This is the velocity along x-axis of point A. Similarly, velocity of point C along x-axis. Now, you see with delta t time, how much distance is traveled by line OB, time delta t. They travel this much. How can figure out this distance? Del U into del T, right? Now, how much distance traveled by line AC? Line AC, they travel from here to here. So what is the blue color distance? That will be this much, right? From here to here. So we can easily figure out because his velocity is this one. If velocity is this one, then this one you time by delta t, you get total distance. Now, how much this distance? Del x, right? So, and how much this distance from here to here is del x. So, distance from here to here, then subtract from here to here. You'll get the line A. 1 second. I have to erase all the line. So line A prime, this much distance I need to figure out, equal to line OA prime, OA prime minus line OA, OA, that we figure out, okay? OA prime minus O, this A, not the this one, okay? I should differentiate with this term. Say if I say A2, this one, this will be A2. Now, what is this distance? OA prime, distance from here to here. Del x, I can say this del x plus this term. So that I did this del x, then plus this term. Then how much is to subtract? Minus this value in minus this value. This one and this one. Then you simplify this term will be out. And this u into delta t, u into delta t out. Then you have on del u by del x into del t. This much length increase, right? But I like to figure out the strain. What is mean strain? Change of length, how much rate of change of length. If I add rate, then it's come with time. But if I like to figure out the strain, only linear strain, you already learned in the solid mechanics. Deformation divided by original length, that will be strain. Strain equal to delta by L, right over here, delta by L. So how much length increase? This much divided by original length along x-axis was del x, but this much length increase. So this is the deformation divided by original length. So you get this one, del t. Now, if you like to figure out strain rate mean there is a t. Okay, is time is over. Can I continue or I should finish it here? You have other class?
Yes, sir.
Okay. Okay. So we are keeping off here. Okay. And we will discuss in the next class. But any question so far? No?
No, sir.